Okay, here we go, 8.2, and today we're using antidifferentiation to work backwards from acceleration and velocity to find a particle's position. So, let's start with Mr. O'Sullivan. He's on a morning run, and we've got an expression for his acceleration. It's cos of pi t. What I'd like you to do then is use the fact that his initial velocity is 3 meters per second, and the fact that he starts at home, to find an expression for his position at time t and to do a sketch of his run. Have a think about that for a few minutes and then start the video again and we'll go through a solution. Okay, so as I think about this, what we're told in the question is that the acceleration is cos of pi t. So x double dot equals cos of pi t. And I know to get from the acceleration to the velocity, I need to integrate. So the velocity is going to be the antiderivative of x double dot dt, which integrating this expression would give me 1 over pi sine of pi t plus c. We're told that the initial velocity is 3, which must mean then that c equals 3. So our expression for velocity is 3 plus 1 over pi sine of pi t. And then we're trying to get up to an expression for the position. The position is the integral or the antiderivative of the velocity. So that's the antiderivative of 3 plus 1 over pi sine of pi t dt. We integrate 3, we get 3t. We integrate 1 over pi sine of pi t. Well, the sine is going to give us minus cos, and then I'm going to get another 1 over pi, give me 1 over pi squared, cos of pi t plus c. Then we also know that he starts at home, so if t equals 0, x equals 0. I'm just being careful here, the first term is equal to 0, but cos of 0 is 1, so x would be minus 1 over pi squared plus c, telling me that c equals 1 over pi squared, giving me an expression of x equals 3t plus 1 over pi squared times 1 minus cos of pi t. And obviously you might have written that without the brackets and all is good. So then it's asking for a sketch of this relationship. Well, with the way that I've arranged it here, we can see that for large values of t, there's a non-vertical asymptote of x equals 3t. So Mr. O'Sullivan is starting at home, so he's starting at the origin, and then we're going to have this non-vertical asymptote of x equals 3t, and then the second half of the expression is going to give me one of those wobbles. And if we think about like the magnitude of the wobble here, well, 1 over pi squared, that's 1 over 9, so it's roughly a tenth. So it's going to be a pretty small wobble. And so what we're going to end up with is something like this. I guess just to clarify, I think I said non-vertical asymptote a couple of times. It's not quite a non-vertical asymptote, this, because we don't get closer and closer and closer towards it. So yeah, that was incorrect language. However, we can see how the long-term behaviour keeps us close to x equals 3t. So starting with that line is really helpful for us to draw it. Okay, so just 2 examples today. Will be a shorter video, but this example gives us an idea of what we're going to be doing here. Repeated antidifferentiation to move from acceleration to velocity and then to position. Okay, you'll have noticed a little jump cut there as I had forgotten about a little typo that we needed to correct. So jumping in on the notes, we have a diagram at the top that illustrates how we move between displacement, velocity and acceleration, and in particular today, if we start with acceleration, we anti-differentiate once to find velocity, and then if necessary, anti-differentiate again to find displacement. So in terms of the first example, we've got Curtis coming out of his specialist maths exam, feeling great, launching his pencil case high into the air. It's a calculator example, so first typo, because we're working with 9.8, you can use your scientific calculator to evaluate the answers. And then second, just to make the numbers work a little bit neater, Curtis has thrown it much harder than 6 meters per second, 16 meters per second up into the air. So with that in mind, pause the video, have a go at answering this question, see if you can figure out how long it's going to take the pencil case to return to Curtis's hand. When you're ready, restart the video for a solution. Okay, so looking at it together, first key piece of information we're given is that the acceleration is minus 9.8 meters per second squared, minus because it's acting downwards. And well, what is x in that case? Well, x is the vertical distance above the point of projection, which is Curtis's hand. So, what do we do? Well, first of all, we're going to anti-differentiate to find the velocity, and if I do that, I'm going to get minus 9.8t plus c. And then using the initial condition we're given, that the speed when t equals 0 is 16 meters per second, that's going to tell us that c must be 16. So x dot is 16 minus 9.8t. And then what we're really interested in for part A is the speed after 2 seconds. So x dot of 2 would be 16 minus 9.8 times 2, so that's 16 minus 9.6, which is minus 3.6 meters per second. But then just attention to detail, it asks for speed after 2 seconds. So the speed after 2 seconds is the magnitude of minus 3.6. So it's just 3.6 meters per second because speed is a scalar. Okay, part B, it's height after 2 seconds. Well, height is position, so I need to anti-differentiate again. Anti-differentiating my expression 16 minus 9.8t. Well, that's going to give me 16t minus 4.9t squared plus c. And since my initial height is 0, because I'm measuring from Curtis's hand, that's my definition, x is 16t minus 4.9t squared. And we want the height after 2 seconds, so x of 2 would be 16 times 2, so that's 32, minus 4.9 times 4, so that's 19.6, so that is 12.4 meters. So a good bit of height. What's part C asking for? C is asking for the greatest height it reaches. So the greatest height would occur when the velocity equals 0. Just before it starts falling, it must pause instantaneously in the air, so when the velocity is 0. So if we look at our expression for x dot, when that's equal to 0, that implies that t equals 16 over 9.8. And then if we substitute 16 over 9.8 into our expression for the distance, so that's 16 over 9.8 times 16 minus 4.9 times 16 over 9.8, and then evaluating that on your calculator, you'll get whatever value you get. So I've just substituted in value of time into my expression for B. and you can do the rest. So part D then, getting towards the end, part D says the time it takes to return to Curtis's hand. Well, at this point you can solve that directly and just work out when the height is going to be 0 again, so that probably is the easiest way to do it. The other way to think about it is to say, well, because of the symmetry of this motion, because it is a parabola, we know that the time taken to reach the ground again, like Curtis's hand, would be the same as twice the time until the maximum height. Time until the maximum height was 16 over 9.8. So symmetry argument would tell us that the time would be double the time it takes to reach the top. So that would be, what, 32 over 9.8. Whatever value you get, approximately, or just over 3 seconds. So, last thing it says in the question, state clearly the assumptions you make in your model. Well, there's a couple of different things we've done as we've gone along. It is important to remember these, to keep track of them. I guess the first is that we're saying that Curtis throws it from a height of 0, so heights are measured from Curtis's hand. So if we were going to correct our answer, if we wanted it from the ground, we'd have to add on a constant value for the height of Curtis's hand, like 1.5 meters or something. And then in terms of general projection motion, the go-to assumptions we have to be familiar with are, well, there's no air resistance. We haven't factored that in at all, so it's a simple model of motion. And the other standard assumption that we can always talk about is that the pencil case is a particle with all forces acting through a single point. No spinning, etc. So one thing that I just wanted you to take from this one, it's really common with projectile motion questions, that the greatest height occurs when the velocity equals 0. So ever you're trying to work out the height something gets to. And then secondly, that through symmetry, to work out the time it takes to get back to the ground or back to the point of projection, you double the initial, the time it takes to get to the top. Okay, good stuff. Now, the second example for today, unfortunately, an error with the printing. It didn't quite print for you guys, but I've got a copy of it for you. And so I just want you to be able to take some notes and take a moment to copy this down and have a go at it. It's a good question going back to the trigonometric functions. So here it is, Eric's yo-yo. We've got an expression for velocity this time. We want a velocity time graph, then a position time graph, and then a description of that motion. So take a moment, pause the video, try this question, and then start it again to go through it. Okay, so the first thing we're asked to do in this question is sketch the velocity against time. So time is always going to be positive, so I don't need to worry about anything to the left of the axis. And I've got this transformation of a cos graph. So first thing we can do is we can figure out what our maximum and minimum values are both going to be 20. So as I'm doing my sketch, I know I'm going to be moving between 20 and minus 20. I think the units in this question are centimetres. Then I can think about the starting position, and I've got the normal cos function, which starts obviously at the maximum amplitude, so it would be 20 in this case, but it is shifted to the right by pi over 4, and so instead of starting at that maximum point, I'm going to start just to the left of the maximum point, and so I'm going to have a graph which starts somewhere down here, but then moves up to the maximum, and then gets me my cycle. And I guess what I'm doing here is initially just drawing the general shape, and now I'm going to work out the details. So first up, if t equals 0, that's going to be cos of minus pi over 4. So t equals 0 implies that velocity is 20 times cos of minus pi over 4. Cos is an even function, so that's the same as cos of pi over 4, and cos of pi over 4 is 1 over root 2, or root 2 over 2. So substituting this in, it's going to be 20 times root 2 over 2, so that is 10 root 2. So that gives me my y-intercept at 10 root 2. Now, in terms of the other major values, if I think about, well, when am I going to get my first value? Well, that's when the argument, the thing in the brackets, is going to be pi over 2. That's when the cos function brings it down. So if the thing in the brackets is pi over 2, add pi over 4 to both sides, so t over 2 equals 3 pi over 4, and then times by 2, so I get t equals 3 pi over 2. So this first function here must happen at 3 pi over 2, this first intercept. And then if I think about then the period, well, because I have t over 2 here, that's going to double the amount of time it takes to reach to cycle through the cos graph. So instead of having a period of 2 pi, it's going to have a period of 4 pi, which means that each of these distances is going to be half of that. That's half a cycle, so this has to be pi. So this point must be 5 pi over 2. Sorry, it's doubled, so it's 2 pi. So adding on, this must be 7 pi over 2. My bad. And adding on again, another 2 pi. That must be 11 pi over 2. And then these maximum and minimum points obviously must occur halfway between those, so between 7 pi over 2 and 11 pi over 2, that must be 9 pi over 2, between 3 pi over 2 and 7 pi over 2, that must be 5 pi over 2, between between minus pi over 2 and 3 pi over 2, this must just be pi over 2. So there's my pretty complete sketch for the velocity. It then asks for a sketch of the position. So it's going to be similar again, but let me do a little bit of work before I get there. So the displacement is going to be the integral of the velocity, the antiderivative of the velocity dt. So it's going to be the antiderivative of 20 cos t over 2 minus pi over 4 dt. If I integrate cos, I'm going to get sine, but because of this t over 2, I'm going to get, I think, 40 sine t over 2 minus pi over 4 plus c. If I just think carefully about what would happen through if I differentiate this, yeah, the half would come out, I would multiply by 40, that would give me 20. This must be correct. So to figure out c, I've given my initial condition. Excuse me. My initial position is minus 20 root 2. So just checking that out, t equals 0, x equals minus 20 root 2 centimeters. If I substitute in t equals 0, this would be sine of minus pi over 4. Sine is an odd function, so that's minus sine of pi over 4, and sine of pi over 4 is root 2 over 2. So x would be minus 20 root 2 plus c, which tells me that c must be 0. So my full expression for the position is 40 sine t over 2 minus pi over 4, and that's what I'm going to try and sketch. So, new graph. This time my maximum and minimum amplitude are going to be 40 and minus 40 centimeters, and my initial displacement, we just worked it out, is minus 20 root 2. I'm going to get my standard sine curve, and then working out the values using similar method to last time, or using the fact that the intercepts here must be the same as the maxima and minima from earlier. I'm going to have an intercept of pi over 2 where the other maximum was. I'm going to have a maximum at 3 pi over 2. I'm going to have an intercept at 5 pi over 2. I'm going to have a maxima at 7 pi over 2, sorry, a minima. So, because it's the derivative, because cos maps to sine with the intercepts matching to the maximum and minimum points, this is quite straightforward to do. And I have my position graph. Part C says, describe the relation between the acceleration and the displacement. Well, we haven't really done the acceleration yet, but the acceleration would be the derivative of the velocity. So differentiating 20 cos t over 2 multiplied by a half, so that's going to be minus 10 sine t over 2 minus pi over 4. And the key thing there is that is minus a quarter times x. And so the acceleration has 1/4 the magnitude of the displacement and opposite direction. Those are really the two key points. It's minus a quarter times the displacement. Okay. Then part D asks us to use all this information we've garnered about this yo-yo to describe its motion, commenting on the maximum and minimum values of position, velocity and acceleration. So as I'm thinking about this, in terms of the position, maybe first of all, it's oscillating between minus 40 centimeters and 40 centimeters. So that might be a good thing to say. The yo-yo oscillates, as yo-yos do, between x equals minus 40 and x equals 40 centimeters. So it has a range of 80 centimeters, which sounds reasonable to me. And it has a period of 4 pi seconds. What's that about? Approximately 12 seconds. Seems kind of slow, doesn't it? For it to get from the same point on the cycle back to that point on the cycle. In terms of its velocity, well, the maximum and minimum velocities for my first graph are going to be 20 and minus 20 centimeters per second. So plus or minus 20 centimeters per second. And they occur when the yo-yo passes x is the point which is at the center of its oscillation, x equals 0, and then the max and min accelerations are plus or minus 10 centimeters per second squared, and they occur at the max and min points, or the highest and lowest points. Maybe that's the best description of the motion we can give, right? We can imagine this yo-yo, and I guess in terms of limitations, the obvious thing about this, if we're talking about vertical motion, we haven't incorporated gravity at all here. So if we were asked for a limitation of this model, it's reasonable for a yo-yo because it's going backwards and forwards, that oscillation, but it's symmetrical, and it's unrealistic with it being symmetrical because we haven't accounted for gravity. Okay, that's us for today. The exercises for this part of 6b just relate to moving from acceleration to velocity to displacement. Good luck with them, and I look forward to seeing you soon.